Is Marie. I'm a postdoc here at the CfA. I'm working in a lab. I have a very exotic title. I will just explain a little bit later. So one of the biggest questions we have is there life out there, outside Earth? Is there life somewhere? Most likely, if we find life one day, it may not be something like that, something very evolved. So what is life? What can we expect? So we need to look at something that are probably smaller. So maybe some microorganisms or some bacteria. Maybe even smaller. We would be happy if we could find traces of DNA. But so far we are really not there yet. We haven't found anything that would be another form of life anywhere else. So what we are looking for as our preliminary step is some molecules that could be life-building fragments. So we would like to find some proteins or amino acids. We still haven't found any of these in space, but we are not so far because we are actually able to find molecules in space. And we've found about 200 molecules so far in the interstellar medium. And those molecules are, let's say, of two types. Those that are stable on Earth, like water or ammonia, methane, and those that are really unstable on Earth, and that surprisingly we find quite easily in space. So radicals, ions, carbon chains. So we have this set of molecules, 200. I don't know if it's a lot or not a lot. It's not bad, but we're still working on this. And they're still quite small. What we see is like from 2, we have a lot of molecules with 2 atoms, to 13, and then 2 very big molecules, and a couple more, but 2 very big, C60 and C70. So C60 is like this buckerball. I don't know if you've ever heard about it, but it's like a soccer ball. Molecules, it's just composed of carbon. And so what we want to do is, from what we see, trying to have an idea of what is going on in space. What are the chemical reactions happening there? And all these unstable species, these radicals, these ions, they are very unstable. They are really reactive and they are intermediate in reaction. So the best picture we have of what is there, the better we can constrain our models of the chemistry in the interstellar medium. And what we want to achieve at some point is to find more and more complicated molecules and organic molecules that could be those building fragments for life. So we are sure that these 200 molecules are there. And how are we sure about it? It's kind of complicated because we can't go there. Like, we can go to the moon, we can come back. So we can bring some samples. In your lifetime, probably we'll be able to go to Mars. Not as sure that we will be able to come back. We talked about it this morning already. We've been to a comet, like Chury. Again, nothing is coming back from this. So we can bring back samples and analyze them in labs. So we need to find another way. And what we can do so far is go to some things that are in our solar system. But all those stars, all those planets, the other things we see, they're far, far away. There is no way that we will ever be able to go there. So we have to use the only information we have from those, and it's the light. We can see them. We have light coming from them. So that's what we do in our field. So whatever it's astrochemistry or astrophysics or astronomy, we use the light we receive from those objects. And what is very important for us is that each molecule has its own way of interacting with light. So this is a very simplistic way of representing things, but if you look at the electromagnetic spectrum, we really well know the visible part, because that's the part we see. It's actually more complex. You have the radiation covers a bigger range, and in each of these spectral regions, you can have some specific interaction with molecules or atoms. So if you use high energy photons, you can interact with the electrons around atoms. And at lower energy, you will interact with molecules. So in the infrared, which is just below the visible light, you can interact with vibration. So literally, if you send a photon in the infrared to the molecules at some specific frequency, you can force it to vibrate, really vibrate. And at even lower frequency, in the microwave or radio domain, you can induce some rotation of the molecule. And in space, all the molecules we've found, they basically have been found through detection in this radio and microwave domain, so at very, very low energy, very low frequency, because that's where we can see the rotational transitions of the molecules, so how the molecules rotate in space. And this is for a very good reason, is because in that spectral region, the spectra of the molecules are specific to each molecule. If you take two molecules, no matter what you decide to choose, they will have different spectra. So all those spectra, they're like fingerprints, they're literally barcodes. If you know the frequencies where your molecule emit or absorb, there is never going to be two molecules that will have the same barcode. So by looking at the spectrum in the sky and by looking at what we know about molecules, we know with 100% certitude that something is there or is not. And this is really powerful because we talked about it a little bit this morning about deuterium, for instance. It's a very tiny change. You also heard about carbon, normal carbon and carbon-13, like we use it for datation on Earth. This is also a very tiny change at the scale of a molecule. You just change one very tiny little bit of something. And then the spectrum is going to be completely different. So we really can see everything, distinguish everything. So that's why we like to work in that spectral region. And so what we do is, first we need to collect some light from the objects in the sky. One problem we have in those domains is like, while we are on Earth, we are somehow polluted by whatever else is happening on Earth. So like radio frequencies, we use them on Earth. We also have light pollution. You have a problem that our atmosphere is not empty. There are molecules in our atmosphere. So if you want to see whatever is in the sky and you have some interacting molecules in Earth, it's a bit problematic. So we need to somehow get rid of it. The easiest, well, not the easiest, the most complicated way, but the one you think first is, let's get out of Earth. So we can use satellites. Put satellites, and then use them to collect light from space. So there was a famous telescope. It stopped working a couple years ago now, Herschel, but it worked for a very long time, and it brought a lot of data. Not all of them are analyzed to date, so it's still a lot of work. There is also a very nice instrument. It's a plane. It's called SOFIA. And that plane is actually flying, and once it's like high, it's literally opening so that the instruments can go out and measure without any window. It took them a very long time to get all the approval to be able to fly like that. Like no flying agency no country would initially agree. So and it's flying in Europe and not in the US because I think there is still some regulation problem in the US, but it's still kind of cool. And the last way, the one that is the most used is ground-based telescopes. But then you have to go quite high in altitude and to some place where there are no cities to pollute you and everything. It's not that easy, but you can have ground-based telescopes. And I'm going to just show you that one, ALMA, because it's the one astronomers are the most excited about. It's still not finished. They are building it. It's going to be the biggest one ever built, the most sensitive one, and the best one in any way. And it's in Chile, so in a desertic region in Chile. And it's composed of 66 antennas. And this, for scale, is a car. So it's just huge. Like another way to show this is like, this is a human person. This is one single antenna, and you have 66 of them. It's huge. So that means it's a very sensitive instrument. It's not finished yet, but they collect already tons of data. So this is one spectrum. So it's a real scientific spectrum that has been published and everything. So astronomers just record the spectrum of one source, one star, one something, and they compare. On the top trace, it's a comparison between the best telescope before and ALMA. So the red one is before, the black one is now. So with ALMA, you have less noise, and you have more points on each line, so you have a better resolution. So you really see more things. And then what they do is they look at databases of every single known molecule, and they look at those fingerprints, those barcodes, and they overlap them until they find matches. And when they have matches, they can assign whatever is there. So I think this is a line of HCN, for instance, and they assign everything they can. They go through the full databases. And when they are done with that spectrum, they just look at whatever was left. And everything that is left is all these U lines, so unknown features everywhere. They're just everywhere. They have no idea of what they are. And the problem is that if they're not in the databases, they just have absolutely no way of knowing of what they are. And those molecules can be super important. They can be the molecules that initiate the reactions, that create things. So this is the big question. We know that 200 molecules are in the interstellar medium. What else is there? And how can we find out what is that? So that's where we intervene in the lab. what we do in the lab, in my lab, it's we study on Earth some molecules, we create the database, we record the spectrum, we create the barcode, and then we send the data to the astronomers and they can overlap them with their spectra to see what they have. So this is one of our instruments, so I will show this afternoon. We have a huge vacuum chamber because we need to study molecules isolated in the gas phase, so we need to pump down our chamber, then inject the molecule we want to study, and then study them in the region we're interested in. And we do this in the microwave, so we just study the movement of rotation of molecules just around themselves. So quick word about the title. It's from my boss. It's a cute title, but it's not that easy. So the boiling oil, it's because we use diffusion pump that allows us to go very low in frequency, so we're literally boiling oil, and the boiling oil is helping us to pump the cell. The jet engines, it's because we use supersonic expansion to inject our molecules in our chamber and cool them down. I will show you this later, just after, actually. And finally, the radar, it's because we use radar technology as a light source, so we use like microwave radiation. So this afternoon, we will go to my lab, and I will show you these instruments, but I won't be able to open them because they're under vacuum right now. So I have a few pictures so that you can see. So this is inside of one chamber. You have one mirror on each side, so they are like quite big mirrors. And the line is bouncing back in between the two mirrors, so that gives us a lot of path, so a lot of sensitivity. And you have this huge hole here. It's because we have a pump below that, so big diameter means very good pumping, efficient pumping. It's also, I don't know if you can see, it's full of oil, so it's kind of dirty. So you really don't want to get in as much as you can. And from the other side, another mirror. And that mirror, you can see many things. You can see a hole there, which is the hole from which we inject the molecules. And it's full of dust around it. It's because usually we do discharge. So we like to excite molecules, break them, build new ones. So we strike discharges, but that makes a lot of deposits, like carbon stuff and everything. So they're just going everywhere. And you also see one antenna. So this here is an antenna from the microwave radiation. The length has to be related to the wavelength. So this is like about 1 centimeter. Well, inches, I can't help. But that's an idea of what we use. And what we do, so it's a very simplistic way of presenting things, but we usually start from stable precursor that we can buy on Earth, because it's easier if you can buy it and if you don't have to synthesize it. And we mix them, and we excite them by any way possible. So usually, let's say, strike a discharge. And then we expand them in our chamber. So by doing this, we can have, in this volume, some remaining lines of the precursor, and then many products that are unknown or somehow not known yet. And the idea is that most of the stable molecules you can buy on Earth, they're already well known. So if they were in space, they would have been found already. So we need to find new things. We need to break molecules, make new combinations that are not stable on Earth. So that's what we do in those instruments. And so this supersonic expansion is to cool down molecules. You have high pressure here, low pressure there. When you have a huge change of pressure, that's help cooling down. And then we study those molecules in that way. So the way we normally work, so it often works like astronomers came to us and they're like, we are sure there is this molecule in space because our models say it should be there. So let's say 2 years ago, we had like a molecule called Si2C. So it was two atoms of silicon, 1 atom of carbon. They say it has to be there, but we don't know where because we don't know where to look because we have no idea of what it is. So can you try to find it in the lab? So we tried. So we started with, you want to have silicon and carbon. So you can try it from methane, which is CH4, silane, SiH4, you mix them, strike a discharge, record the spectrum. Then we also need to know where to look at approximately in the lab, so we use theoreticians that do some calculation or where the lines are supposed to be. And then we eventually found them, so that was cool, found them in the lab, gave the data to astronomers, so really give them a barcode. They just overlap with their spectra, and they find 100 match. So 100 lines in common between what we had in the lab and what we had in space. So they were right, the molecule was there, but they just didn't know where to look at. So that's it until we see the lab. The idea is just, no matter what we are going to do in the future, the only way we will be able to ever say there is life outside Earth is going to be through spectroscopy. So spectroscopy is really the science of how molecule and matter interact with light. Because light is always going to be the only information we can get from these objects. And I'm done. Yes, so that's a big problem. So silane can explode. So the only way you are allowed to have silane in a lab is to have it not pure. So you work with like 1% silane and everything. It's a big security problem. Somehow we manage. Pure silane, no one would be very comfortable with it. I think if you're below 1%, there is basically no chance anything bad could happen. Or if anything bad could happen, you just will blow up your experiment and not the full building. Which is not so bad.
We use it for supersonic combustion. So we get silane with hydrogen and oxygen at very high speeds, supersonic speeds.
Yeah.
In order to get some of the hydrocarbons to burn quick, within the combustion chamber. So when you say silane,
yeah. Silane is nice, but dangerous.
Question. In the spectroscope, so you said you had all these unknowns, right?
Yeah.
So, is there any predictive, like if you know a molecule that has one signature,
Yeah.
can you predict if you modify the molecule in a certain way, what would be the next one?
Yeah. So actually, yes. Computers are really, really good now. So quantum chemical calculation gave very, very good predictions. The only problem, if you just look at, so you still have some tiny error on whatever you're going to predict. But that tiny error is really big enough to have a couple of lines, maybe 5 lines, in the astronomical spectra. And then that's almost impossible to make this arbitrary choice. I'm going to choose that one. So it's easier in the lab because in space, they see this, when they look at their spectrum, they contain 100 maybe feature, like 100 different molecules. So it's a big soup. In the lab, when we do this, maybe we have 10 or 20 molecules at once. So it's less dense. So even if we have a prediction that is a little bit off, maybe there is only one candidate, at worst 2. So we can start finding things. So yes, we use calculation. And once you know something, it's much easier to get to the next one. Like, let's say you change carbon 12 for one carbon 13. This is very fast to do in the lab. But in space, still very complicated if you don't have a support from lab.
How many times do you have to repeat in order to say, okay, I got this combination?
So it depends. So we have 2 ways of, so if you have only one line, there is no way of knowing what it is. You can't assign anything based on one line because you can have coincidence. So the only way to be sure is to find like redundancy, a pattern, like you find at least 5, 6, 7 lines in common. So it depends. If we do very high resolution things, you can find one line very fast, so in like 10 minutes, but then you have to repeat this for every single line you're going to use. We can also do like some broadband measurements. We record a very large region. Then you have tons of lines at the same time, but then you have a lot of noise. So it's going to take longer, not because you don't have information, but because you have to average to have this noise going down to be sure what you're seeing. So usually when we work on one molecule in the lab, it can range from 1 day to 1 year, depending on how complicated it is. And the good projects are the ones we can do in 1 week. This is what we like. It's not often. And yeah. But then the actual experiment on one line can be from 5 seconds, sometimes it's super strong, to 24 hours of ranging on the same feature.